Hi everyone, in this lesson we're looking at higher order derivatives, and I have a table right here. First of all, we have some notation. So this means find the first derivative, find the first derivative, find the first derivative. But we can also extend it and take a derivative of a derivative. So if we take the derivative of the first derivative, that's the second derivative. If we were to take the derivative of the second derivative, we would get the third derivative, and so on. And this is the notation for that. So usually in your physics classes, you may have already looked at this. The original function, the position function, would be represented by, just y equals f of x. And if we take the first derivative, we'll get velocity. And if we take the derivative of the derivative, in other words, the second derivative, we would get acceleration. And so there is real world applications to using higher order derivatives. And this is the notation. And you would just do double or triple tick marks up until you get to the point where you're 4 or more. You could use Roman numeral notation, or you could just start writing it to the 4th, to the 5th, and so on. Right? We also have the dy dx, d squared y dx squared. These all mean the same thing. So let's take a look at an example. We want to find the fourth derivative of this function. So we're just going to take the first derivative to start using the power rule. Now we're going to take the second derivative. So in other words, we're taking the derivative of the first derivative. Now we'll take the third derivative. That means we're taking the derivative of the second derivative. And finally, we'll take the fourth derivative, meaning we'll take the derivative of the third derivative. The derivative of a constant is 0, so the derivative of 12 is 0. So our final answer here is negative 120x. All right, on this next page, we have distance, velocity, and acceleration relationships. S of t equals the distance as a function of time. If I take the derivative of s of t, I'll get the velocity as a function of time. If I take the derivative of v of t, which is really the second derivative of s of t, I'll get the acceleration as a function of time. So first derivative, velocity, second derivative, acceleration. So let's take a look at some problems here. Because the moon has no atmosphere, a falling object on the moon encounters no air resistance. In 1971, astronaut David Scott demonstrated that a feather and a hammer fall at the same rate on the moon. The position function for each of these falling objects is given here, where s of t is the height in meters and t is the time in seconds. Find the acceleration. So in order to find the acceleration, we need to find the second derivative of the s of t function. So let's write out s of t. And we're going to take the first derivative of that. The first derivative is going to be the velocity. And now we're going to take the second derivative to get the acceleration. So we get negative 1.62, and that's meters per second squared. All right, moving on to number 3. An automobile's velocity starting from rest is v of t equals 200t over 3t plus 1, where v is measured in feet per second. Find the acceleration at 5, 10, and 20 seconds. So we want to find the acceleration where we have velocity, so we need to take the derivative of the velocity function to start. So the first derivative of the velocity function gives us acceleration. Now we have a quotient, so I'm going to use the quotient rule. And now we'll simplify the numerator and simplify it one more time here. So we know that the formula for acceleration is 200 over 3t plus 1 squared. And we're being asked to find the acceleration at 5 seconds, 10 seconds, and at 20 seconds. So all we have to do at this point is input 5, 10, and 20 into the acceleration function. So the acceleration at 5 is equal to 0.78 feet per second squared. Input it for 10. We input 10, we get 0.21 feet per second squared. And then now we'll input it for 20. And when we input 20, we get 0.05 feet per second squared. All right, nice short lesson today. Hope you enjoyed it. Have a great day.